I feel much better today.
Aye.
Not nearly as tired as yesterday. I was just totally out of it.
You're running out of adrenaline.
Today I should be okay.
I'm just gonna just introduce you.
Okay, so you want me to sit somewhere else or?
No.
And I'll be in the back over there, just in case you need anything, but.
Yeah, if something
Good to
goes
go.
wrong.
Yeah, yeah, exactly.
Okay, thanks. Hey, Paul. Okay, I'm gonna introduce my family, so. What's that? He said new face in the crowd. I'm still eating, I guess.
Yeah.
So Carl, did you take the shingles vaccination or not?
I had them, yeah, I had the new ones, the 2 vaccines. And so it's a very mild case actually, but it's shingles.
Yeah, I've never heard anything.
It doesn't hurt at least, it only itches some. And it's going away now, so. I've been taking these antiviral pills. Which I get- I'm sorry, for the shingles, yeah. But I also had a cold sore that gets rid of those too. So, it brings me a glass of water or something I might need it later.
It doesn't, but she's out today. I can go grab your bottle.
Actually, I think Rashid was gonna get me something, maybe he'd bring it. Yeah. Early, you know, a glass of water.
Mike Farrell was the second. I don't know how you did. I don't know.
Good.
Yeah.
I was just gonna cut in my hand. It's good.
Well, it was great. When you brought us down. It's hot. No questions. No.
Hey,
What kind of pictures would you like? Would you like it just off
Whatever.
the slides? I don't know if this is like proprietary info.
no, it's whatever whatever you want.
Okay. They're gonna film it, so someone else will be doing the video.
Yeah, okay. Yeah, we want to send that to some of our Carol's children and so on. So.
Smile.
Oh, my goodness. Okay. Good stuff. I guess Alex is bringing me a glass of water. Oh, okay. He'll be back in a shortly, hopefully. People still coming in, I guess. Glad Maury came.
Having the reception upstairs a little bit downside.
Sorry?
Having the reception upstairs.
Yeah.
Big startle.
Yeah. Need the water right away, but And start till 5 after anyhow, guys.
Used to visit in Michigan. They used to start everything late, like 20 minutes late.
Wow.
Classes, everything.
Huh.
And they called it Michigan time. And then their president said, no more of this silliness. We're gonna start. Didn't work, yeah.
Oh, thank you.
Yeah, they'll realize it. It feels very- Exactly. No.
All right, if I could have everyone's attention, welcome everyone to this occasion. I get to introduce a fair number of speakers that I host, and it always starts with something like, it's my honor or privilege to introduce people. And it's always kind of, there's different levels of honor and privilege, right? You can say that. Introduce that, but this week it really is a great honor and a real privilege to introduce our own Professor Carl Koch. You've probably seen this, but this is part of a new lecture series that Carol and Carl have endowed, aptly called the Carl and Carolyn Koch Lecture Series, and there's more after that. It's in areas that honor. It's in areas that emphasize the areas in which Carl has made contributions over the entirety of his career. So it's a very broad area, but this will complement the spring distinguished lecture series that we have, the Davis Lecture Series. So we're going to have fall and spring. So we're balanced, and we're very happy to have that generous endowment, and very excited about that. And it will maintain President Cook's legacy here for decades to come. Excited to get that started, and excited to have the very first speaker being Carl Koch. So Carl received his PhD in metallurgy from the Case Institute of Technology, now Case Western Reserve University, in 1964. He was a postdoctoral NSF fellow in Birmingham University in the UK. He joined Oak Ridge National Laboratory as a staff scientist in 1965. He was a group leader in the superconducting materials and then the alloying behavior and design group before he joined North Carolina State University. And Carl has some stories of being talked into coming to NC State and when the department was going through a big expansion back in 1983. He's currently Kobe Steele Distinguished Professor of Material Science and Engineering. He's made significant contributions to the understanding of mechanical alloying and the preparation of amorphous and nanostructured alloys. His recent research interests include studies of high entropy alloys. And one of the things that has been a hallmark of Carl's career, if you look back over it, is he's always in the beginning of new fields, all the way up from the beginning to the final kind of late career things. And one of the first to recognize high entropy alloys as a new field of study. So that's always exciting to have worked and seen these new areas come through Carl's involvement. He's published over 360 papers, edited, co-edited 7 books. He's achieved the rank of fellow in 5 professional societies, including the Minerals, Metals, and Materials Society, the Materials Research Society, the American Physical Society, ASM International, and the American Association for the Advancement of Science. He was also elected into the U.S. National Academy of Engineering in 2013. This is one of the highest honors that we can get in our field. Not listed here are numerous university things, the Reynolds Award and the Holiday Medal and all sorts of things that Carl's had throughout his career. So again, thank you very much, and it's a real honor and a pleasure to introduce you.
Thank you very much, Don, for the great introduction. So here's the title of my talk: From Metallurgical Engineering to Material Science and Engineering, Lifelong Learning and a Changing Profession. So as Don said, this is the first in the Carl and Carolyn Koch lecture series. And before I get going, I'd like to introduce my family. And of course, Carolyn, who's my partner in this endowment, and my wife. And then my older son, Paul, Paul got his bachelor's and master's degree in civil engineering here at NC State. And he's vice president of his company, Stantec, large engineering company. My younger son, Alex, next to him. Alex got his BS and MS degrees in exercise science at Appalachian State. And he got his PhD at the University of Kansas. And he's a professor at Lenore Ryan University in exercise science. He's the weightlifter. And then his lovely wife Allison next to him there. And she also has a PhD in nutrition, and she works for a company that is run by Mark Cuban. Everybody knows his name. So in our family, we've got athletes beside who, and I'm not one of them, but Carolyn was a very good figure skater. She was an Olympic judge and so on. And Alex, of course, was a weightlifter, competed in the weightlifting events and so on. Okay, well, let me start. So this lecture series, as Don pointed out, is going to emphasize outstanding contributions to understanding processing structure and or properties of metallic materials. So since I'm an old metallurgist, I want to keep metallurgy kind of as one of the focuses in our department. And so this talk's going to describe how the discipline of material science and engineering evolved. And then, and maybe this is going to bore some of you, but I'm going to, as an example of my career, present the need for lifelong learning in our profession. Some of this is sort of egotistical and a little nostalgia for an old man at the end of his, or toward the end of his career. So the outline, first of all, I'll talk about a little bit what defines an academic discipline. And then I'll take a little excursion and talk about materials and how they've affected civilization. And then I'll get into the evolution of engineering education, and then get more specific and talk about the evolution of material science and engineering and material science and engineering education, and briefly talk about how professional societies and journals have also evolved in this regard. And then I'll spend a fair amount of time on my personal career history, as I say, an example for the need for lifelong learning in our profession. I should point out, I came down with the shingles last Saturday. I'm recovering, but if I get tired, I may sit down. But right now, I seem to be okay, much better than I was yesterday. Oh, wait. Okay, so what defines an academic discipline? Well, late Robert Kahn, who was a major material scientist at the end of his career at Cambridge in England, he wrote an excellent book called The Coming of Material Science. And if any of you are interested in looking at real details of how our career evolved, I certainly recommend that book. And in his book, he quotes John Simon, and some of you may recognize his name. He's a famous solid-state physicist, on the definition of an academic discipline. Simon says an academic science is divided into disciplines, and each one is recognized domain of organized teaching and research. Well, besides looking at this in terms of academia, we can also look at this in terms of the profession in general, whose members may be in academia, but also in industry or maybe government labs. I'm not working quite right here. What should I be pointing at? At this or? Okay, that'll work. Simon's definition of a discipline and what makes up a profession. What he says is that it's a discipline more than just a conglomerate of university departments, learned societies, and scientific journals. It's a so-called invisible college whose members share a particular research tradition. However, I think it's also convenient to talk about this in terms of a university program department, and then the professional societies that serve the discipline, and then the journals that record the scientific and engineering progress in the field. So that's what I'm going to get into. But before I do that, I'm going to digress a little bit and talk about how materials have influenced civilization. Now, many years ago, I taught a course for our honors program on sort of how materials influence civilization. And so this is something that's always interested me. So as most of you probably know, archaeologists and historians usually classify the ages of ancient man into the important materials that were dominant. So we have the old stone age, the Paleolithic, from about 2 million to 40,000 years BC. The new Stone Age, the Neolithic, where the stone tools were refined and made more sophisticated and so on, from about 40,000 to 8,500 BC. Then we have the Chalcolithic, where people started to use metals, copper, along with stone, from about 8,500 to 3,000. And then we have the Bronze Age, from about 3,000 to 1,200 BC. Then we have the Iron Age, again, about 1200 BC, about to the Roman Empire, maybe. And of course, during this later time, other materials, of course, wood was used early on, even in the Stone Age, of course. But then textiles and glass, concrete, and so on were developed. What we might call the Age of Steel didn't start until much later, even though the ancients figured out how to make steel. They couldn't make it in very large quantities. It wasn't really until Bessemer in 1850, in the 1850s, came up with a way of making a lot of it. And so steel became the material of most interest at that period, from about 1850 to 1965. And why I chose this date, 1965, that's when the number of publications on steel dropped below those on silicon. And so from 65 on, we might call this the age of silicon. So a very nice description of the role of materials on the developments of civilizations. On a book I used as a textbook and when I taught this honors course. But it's really for the layman. You don't really have to have a technical background, and a lot of the honors students that took my course, were not in engineering or science disciplines even. But I gave them a little basic material science along with it. Stephen Sass, who is a material scientist, I think he's probably retired now. But he was a very good electron microscopist at Cornell, and he wrote this very nice book. Again, if you're not a material scientist, or even if you are, it's an interesting one on the history sort of materials and how they influence civilization. Okay, well, unfortunately, instead of a metal, sort of the first material that was a success in what we might call materials engineering was a ceramic. And of course, it was discovered by heating up clay, which you all know is nice, soft, gooey material that you can form into different shapes. And the reason it can do it is because of this structure. It has a nice layered structure, so you can easily split the layers by one another. And the interesting thing is, if you take clay and make it into a shape like a pot or a sickle or whatever, you heat it up, it turns into a brittle, hard ceramic. And so these materials then really helped shape the agricultural civilization from the hunter-gatherer life, because now you could store things in pots and use these sickles to get your grain cut and so on. Okay, well, smelting of copper, something that's very interesting to me. I'm sure I got the right one. Works half the time. Anyway, the fact that you could get this reddish ductile metal out of a rock, to me, is still fascinating. And of course, we don't really understand how ancient people came up with this, but probably a serendipitous event. And of course, unlike many of the noble metals, copper is an element that sometimes can be found free, like in stream beds and so on. And so the ancients did find pieces of it and could use it for jewelry or decorations. And how early man discovered you could get this by heating up certain brittle rocks remains a mystery. But one suggestion is maybe a potter was decorating his clay pots with this attractive mineral malachite. And I'll show a picture in the next slide of it. It happens to be a copper ore, copper carbonate. And so when he heated this up in his kiln to make his ceramic pot out of clay, when he opened the kiln up later, he found these nice reddish ductile metal droplets in the bottle, and maybe he was smart enough to figure out maybe these things came from the malachite. Well, who knows? So anyway, here's a picture of malachite. And so you see it is a nice, pretty turquoise mineral. And then here's maybe what might be a very primitive copper smelting furnace. That's the next one. This darn thing is not working very well. Sorry about that. Well, some of the first copper ores that were used by the ancients, pure copper, not very strong, although if you beat it, you can work hard on it and you can use it for some things. But some of the ancients found that some of the ores contained arsenic. And so basically the first copper alloys we know about were copper arsenic alloys. So that one thing, the ores were limited. And of course, there are health problems associated with arsenic, as you well know. And when you heat it up, you could get volatile arsenic trioxide. And so, some of the people who were doing this work got sick or died. And so clearly you wanted to find something better than arsenic as an alloy. And they found that if you added tin to copper, you could get a stronger alloy, which we call bronze. And so then with bronze, ancients were able to make much better weapons and tools, which were difficult to produce from stone and copper. This thing's just not working.
Maybe line of sight here where the computer is. If you're closer to that computer, maybe the desk is blocking it out.
You can also use the
I can
arrows
use
on the
this.
keyboard.
Okay.
Yeah,
Yeah, that's better.
just move it over here.
Okay, good. Thank you. Okay, well, there's just a picture of some bronze artifacts and some bronze tools. That's not working either. What? Okay, well, let me see. Where was I? Okay, there's the next one. I just have to be over here, I guess. Okay, so now iron presumably should be stronger than copper alloys and bronze, but a lot more difficult to extract. And of course, one reason is the melting temperature of iron is much higher, about 1500 or something, 1536. This is much higher than the typical charcoal fires that those early craftsmen had, which maybe only went to about 1200. But 1200 was enough heat, you could reduce iron from its ore, from its oxide ore, so you could end up with iron, but it was typically mixed with unburnt charcoal and oxide and silicate impurities, slag, and so on. So I have this nice ductile iron with a bunch of brittle crud, but then you could hit it maybe with a stone hammer or whatever and end up with getting what we call wrought iron. But it turns out wrought iron, which we still make today for decorations and so on, is nearly pure iron, and therefore it's not as strong as bronze. But again, maybe somebody figured out that if you heat up iron in a carbon atmosphere for a long time, and some of the Romans believed actually that you were purifying iron. Of course, actually you were alloying it. You were putting carbon in and making what we call steel. And so this turned out to be very strong. And of course, if you heated it up to a high temperature and then quenched it in water, it got very hard and strong, but very brittle. But then if you heat it up at a lower temperature for a while, it got a little less strong, but got tough, like what we call quenching and heating, tempering. And so probably the Romans figured out how to do that. But the ancients' first contact with iron was presumably in the form of meteorites. Interesting, in the latest National Geographic, they're talking about King Tut's artifacts in the King Tut's tomb. They found a little iron figurine that presumably was made from a meteorite. And interestingly, apparently the ancients even knew that these came from the sky somehow, because the Sumerian term for iron was heaven metal, and the Egyptian term was black copper from heaven. Well, the Hittites apparently they established an empire in what's now north central Turkey around 1600 BC. And it's believed they were sort of the first people to actually understand the production of iron from its ores. And it also is highly regarded in their society. So iron was often looked at with more regard than some of the precious metals. But then this knowledge spread to the rest of the Near East after their empire fell. But iron smelting was also independently developed elsewhere. For example, in China, and China apparently came up with the first cast iron, the first primitive blast furnaces. And interestingly, what is now Nigeria. And the quenching and tempering of steel was probably not known, however, until the Romans figured it out. Well, during the ancient times, the Middle Ages, the people who did all this presumably developed our metals, and eventually through trial and error and so on, they came up with better ways of doing this, of a blast furnace and steel. But as I said before, it really wasn't until the 19th century that it was able to make steel in large amounts. And that was Henry Bessemer in about 1855. He developed the Bessemer converter, and this took the advantage of the strong reaction that exists between carbon and oxygen. So he devised a method to decarburize the pig iron, which usually has way too high concentrations of iron, 3 or 4%, makes it very brittle. So he could get rid of the carbon by blowing a blast of hot air through the molten metal. And of course, there have been subsequent developments, the open hearth, electric furnaces, and so on. So large tonnages of steel can now be produced, and almost 2,000 million tons in 2021. So next to concrete, it's certainly the most popular structural material. So now I'd like to talk a little bit about engineering education. So of course, we know engineering was carried out in ancient times from the examples that we see, the temples, palaces, bridges, aqueducts, and so on. But unfortunately, there's very little known about the actual engineers who carried out such projects. There are a few names, though, and the oldest is probably Imhotep, about 2750 BC, and then some other Egyptians later, like Inini and Sunamut. And these were architect engineers, and they were involved in designing the pyramids. And they presumably they were nobles who were in the pharaoh's inner circle. And in the education was no doubt by private instruction, maybe carried down father through son, or maybe apprentice periods. Interestingly, Imhotep was supposedly also the first known physician. So he was both the first engineer and the first physician. So you might say he was a Renaissance man, thousands of years before the Renaissance. Although there was a lot less knowledge about engineering and medicine, so maybe one person could know it all then. Well, engineering was really not part of the Greek academies. They tended to look down on engineering as a craft and so on. And of course, Archimedes is probably the most famous Greek engineer. And Tark says that Archimedes didn't really consider his engineering work too important, but that I think some scholars think maybe Plutarch may have been wrong, and Plutarch tended to exaggerate things anyway. But in any event, Archimedes did a lot of good engineering. And of course, there were a lot of impressive engineering works carried out by the Romans, but not a lot of record about names of people. And often councils who were in charge of projects took credit for them, even though they weren't the engineers. And of course, ancient China had many engineering accomplishments, and the engineers were typically officials of the emperor's court. Okay, so talking now again about engineering education. The 7 disciplines in the medieval universities, as you can see there, did not include engineering. And so presumably engineering education still involved apprenticeships and the guild system. But of course, we look at the Gothic cathedrals and so on, and we know there was very significant engineering going on. But the first formal schools of engineering really began in France in the 17th century. And they were first for military engineering, but then later kind of expanded to bridges and roads, what we call civil engineering now, which my son Paul is a civil engineer. Well, of course, the Industrial Revolution, a lot of the innovations occurred in Britain, but apparently most of these engineers who did it learned their knowledge from crafts rather than formal schools. But the Royal Military Academy was established in 1741 in Britain. And in America, George Washington pushed for establishment of an engineering corps during the Revolution. He recognized how important engineering was to the military. And of course, he had the background. He'd done surveying when he was a young man. And so he already had a background or interest in engineering. And of course, he recommended the establishment of a military school in West Point, which later came into existence when Jefferson was president, 1802. And so West Point was really the first engineering school in the US. Well, Rensselaer School, another early one. Now, of course, it's RPI, established in 1824. And it first mentioned the term civil engineer in its catalog in 1828. And so during the 19th century, other engineering disciplines began to be taught along with the military and civil engineering. And the first course of metallurgical engineering was actually given at the University of Michigan, 1854. Of course, Michigan in those days was a big center for mining, iron mining, especially in the Northern Peninsula and so on. And so toward the end of the 19th century, traditional engineering disciplines we recognize today, like civil, mechanical, electrical, chemical, were finding their places in university curricula. And metallurgical engineering typically was an offshoot of mining engineering. So let's look at metallurgical engineering then. Well, mining, extractive metallurgy, process metallurgy, of course, was carried out from ancient times. All these people that figured out how to smelt the metals out of ores and so on. But it was mainly a craft, an art, basically until the late 19th century. And there's a book called De Re Metallica by Georgius Agricola. That was his Latinized name. He was actually a German. His name was Bauer. And interestingly, it was translated from the Latin by former President Herbert Hoover and his wife. Of course, Hoover was a very successful mining engineer before he got into politics. And interestingly, when I first joined PMS, the Metallurgical Society, as a student member in 1957, they gave all of the student members a copy of De Re Metallica. So I got a copy of it then. And you can get it now for about $15 on Amazon. But in any event, this book basically described mining and extractive metallurgy up to the time it was written. And at about the same time, another book was written by this Italian. Well, more recently, of course, there are a number of modern books on the history of metallurgy. For example, Robert Franklin Mayo in 1948. And Mayo, of course, was a famous metallurgist at Carnegie Tech, now Carnegie Mellon. Sir Stanley Smith, a number of books. He became really the well-known a person in terms of the history of materials. He was at MIT, and then UK R.F. Tolkien. Okay, so now let's talk about the evolution of material science and engineering. It turns out industrial laboratories like General Electric and DuPont had a history of using multidisciplinary research to solve material problems. And this approach really was accelerated after World War II. And really notable examples are Bell Laboratories and GE. Well, Bell Laboratories, of course, became maybe the best solid-state physics lab in the world. And with the invention of the transistor and some of the people there, like Bardeen and so on. And then GE, after the war, a former Army officer, Holloman, was given management of the research lab. And his management philosophy was hire the best people you can and basically leave them alone. And that's what he did. And it was very successful. And so a lot of the seminal work in our field, people like David Turnbull and John Kahn, was done at GE's research lab in those days. Of course, in the good old days, most industrial companies had good fundamental research labs. And then the national labs that were established after World War II with funding from the Atomic Energy Commission. So laboratories like Oak Ridge, Argonne, Brookhaven, they all had significant multidisciplinary materials research efforts, and also the weapons lab, Los Alamos and Livermore. And also major materials research conducted in government labs, like the Naval Research Lab, where Don came from. Okay, so how did materials and science evolve in universities? Really started at Northwestern under the leadership of Dr. Morris Fine. And turns out Dr. Fine was a metallurgist who had come from Bell Laboratories. And he therefore had been exposed to interdisciplinary research. But he was asked to start a graduate program in metallurgy at Northwestern in 1954. And so when he got there, he pushed for a graduate program in a broader sense, looking at all materials, material science. And also Professor Jan Frankel was also interested in doing this in the undergraduate program. So this was how it happened. And the graduate program in metallurgy changed its name to material science in 1959. That happens to be the year I got my bachelor's degree in metallurgical engineering. So then, while universities started to change, many departments broadened from metallurgical engineering into material science and engineering. MIT in 1967, NC State in 69. Professional societies devoted to metallurgical engineering also started broadening, and these included TMS and ASM International. TMS was part of the American Institute of Mining and Metallurgical and Petroleum Engineers. And in 1957, when I joined as a student member, actually, TMS became the Metallurgical Society of AIME. But then they changed to being the Minerals, Metals, and Materials Society, or TMS, which is it is now. And ASM was originally American Society for Metals, but now it's just ASM International, and they look at all material classes also. Some of the other materials societies kept their speciality, however. And then we have a new material science society, the Materials Research Society, MRS, started in 1973. And so that was from the start interdisciplinary. Some professional journalists that were previously focused on metallurgy also broadened into materials. And for example, this very prestigious one, Acta Metallurgica, for a few years changed to Acta Metallurgica et Materialia, and then finally just changed to Acta Materialia, which it is today. Okay, so now I'm going to, for the rest of the talk about my career. as an example of how one really has to keep learning through one's life. And so I began college in 1955 as a freshman at what was Case Institute of Technology. Now it's the engineering school of Case Western Reserve University. Case was an engineering school founded in the late 1800s, and there was first, I guess, Case School of Applied Science and so on, and then it became Case Institute of Technology. Interestingly, of course, the Michelson-Morley experiment was carried out. Michelson was a professor at Case, Morley was at Western Reserve, and that's where the Michelson-Morley experiment was carried out, which at least maybe Einstein knew about it, but in any event, it showed that, you know, the ether didn't exist. In any event, the freshman year was common at Case. At the end of the year, I decided to major in metallurgical engineering. And that was for several reasons. I had a good friend when I was in junior high, middle school, as they call it now, whose father was a mining engineer, and they gave me a bunch of literature on careers in the mineral industries. And then my science class in junior high got to spend a day at Case to learn about engineering, and we got to pick a department to spend the afternoon in. And I guess because of the background I had from my friend's father, I decided to visit metallurgical engineering. The department head, Doc Donaldson, was a real character, and I guess he impressed me. And then the present department head, when I was a freshman, Alexander Troiano, made a very strong case for this curriculum to the freshmen. So I ended up going into metallurgical engineering. Here's a picture of our old metallurgy building. I ended up getting scholarships. Doc Donaldson won my sophomore year. And then the Cleveland Twist Drill one, my junior and senior years, was a very nice one. It paid my full tuition, and they also gave me a summer job. Of course, the idea was I was, you know, might go to work for them afterwards. But I decided I really wanted to do more sophisticated research, and so I applied to graduate schools. And while I received an offer from MIT, I decided to stay at Case for several reasons. One, Troiano really tried to keep me there. He gave me a project my senior year that could be part of my master's thesis. Then personal reasons. And one of the personal reasons was I was dating a girl at Western Reserve who I was serious about, happens to be Carolyn. And then she broke up with me. I'll point out later what's happened since then. So graduate research at Case, Troiano was my advisor, and my master's thesis was on the effect of retained austenite on hydrogen embrittlement. I got my master's in 1961. Troiano at that time was one of the experts in sort of hydrogen embrittlement in steels and other materials. And my PhD thesis was on strain aging embrittlement and delayed failure. Got my PhD in 1964. In those days, most of us at Case had what were called graduate assistantships. And those allowed us to only take 2 courses per semester. So it took 4.5 years to get all the coursework in those days. And if you were asked, you taught a laboratory course. So it's kind of a combination, what we call, you know, assistantships and teaching assistantships. And if you were asked to teach, you did it. And since I came as an undergraduate there, I basically taught a course every semester. And we worked a 40-hour week. I mean, we were paid for, and sometimes more. But the good thing was we were paid about what a starting BS graduate engineer made in those days. So, you know, it was a pretty good, I was able to save some money in grad school. Okay, so we moved to a new metallurgy building, which was built just behind the old one. They tore the old one down, and we moved in 1961. And in those days, steel was king. Most of our research was on structural materials and mostly on steel. And I like this little poem by Rudyard Kipling. Gold is for the mistress, silver for the maid, copper for the craftsman cutting at his trade. Good, said the baron sitting in his hall, but iron, cold iron is master of them all. And certainly in those days, steel was king. But during my graduate program, evolution toward material science was occurring. We had a lot of new faculty who would come from the UK, the so-called brain drain. And then they put up a new material science building right next to our metallurgy building. And the first director was Professor Don Gibbons. He was actually from Britain, got his PhD in Birmingham in metallurgy, but he'd done mostly solid state physics work at Bell Labs. And I took a seminar course on band structure metals from Gibbons. Should point out, I minored in physics when I was in grad school. We had a minor in something, and I chose physics. I had to take the physics qualifier. It was only undergraduate physics, fortunately for me. And then polymer research started in the material science building with Professors Eric Baer, Phil Guile, and Jack Koenig. And it turns out Eric Baer was actually a member of my PhD committee. And of course, he eventually developed the macromolecular sciences department at Case, which was one of the better ones. And that's where our former professor Maury Balick got his PhD. So I got my degree in '64, and while I interviewed some industrial labs, I decided I probably needed a postdoc to enhance my chances to get a good research job. And I had offers from a number of US universities, and probably the most prestigious one was from UC Berkeley. But I was fortunate to get an SF postdoctoral fellowship, and I decided to use it at a university in the UK. Professor Zaki at Berkeley tried to talk me out of it. He said there's no university in the UK any better than Berkeley, but I didn't believe him, so I ended up going to Birmingham. So here's a picture of University of Birmingham from the sports field, rugby. Some of the grad students there played on the rugby team. I used to watch them. But I went to Birmingham in September '64, worked for Dr. G.B. Rayner on the topic of alloying behavior of infra-rare earth alloys. Rayner was the department head, and he'd been a former student of Dr. William U. Rothery, who I think we consider the father of alloying behavior. And the goal of this project was to determine the electronic changes that occur in cerium depending on its environment. Cerium, at the beginning of the rare earth lanthanide series, has one 4f electron, and it can be promoted to the conduction band, changing the valence from roughly 3 to 4. And our experimental approach was to alloy cerium with other rare earth elements like gadolinium, and then precisely measure using X-ray diffraction the lattice parameters as a function of alloy concentration. And this allowed us to calculate the atomic volume of cerium, which then reflected its electronic structure. And we also carried out magnetic susceptibility measurements to try to confirm what we found. So the interesting thing, the postdoctoral year at Birmingham exposed me to the British tradition of physical metallurgy. Of course, in those days, there were no graduate courses. All they did was a thesis. And typically, a master's thesis, they built a fancy piece of equipment that they then used to do their PhD work. I ended up building a little annealing furnace, at least. And also, interestingly, I was able to meet Professor Hume Rothery. Jack Christian, who's a professor at Oxford, has done his sabbatical in Case while I was there. And he was back at Oxford, and he was my host, and he introduced me to Hume Rothery. Hume Rothery had been deaf since a teenager, but he could read lips very well. And even though you were supposed to write things for him, he usually knew what you were saying well before you wrote anything. And so of course, he was a great guy. And of course, the other major thing about my year in England was I met my wife, Evelyn, who's the mother of Paul and Alex. And we were married for 50 years. Unfortunately, she became ill and passed away over 7 years ago. And I reconnected with Carolyn, my old college girlfriend, and now we're married. So, so after some interviews on returning to the US, I accepted a position at Oak Ridge National Laboratory. Here's a picture of Oak Ridge in those days. This is the big parking lot. Now it's filled with buildings. And I worked in buildings back in this area. And I was in a group studying superconducting materials. And so this was another major learning experience for me, because my only exposure to superconductivity was a few lectures in a solid state physics course I had in graduate school. So I had to learn a lot of new concepts in the field of superconductivity. Also, the experimental low temperature physics, experimental methods, how to handle liquid helium and so on, measure the various superconducting properties. And so our charter was to study the structure property relationships in superconducting materials that determine the magnitude of the critical current density J sub C. This parameter, of course, is important to maximize to allow for construction of high field superconducting magnets that needed for fusion energy research and accelerators. Of course, the biggest use of superconductors are in MRI magnets, but they don't have to be, quite as strong, but it helps. So, superconducting research. So this, first of all, this is a picture of a fluxoid lattice, which I'm going to talk about. This was imaged by nanoscale ferromagnetic particles attracted to the fluxoids. So it turns out there are two kinds of superconductors, type 1 and type 2. Type 1, when you apply a field, it's a perfect diamagnet. It excludes all the field from the material until you reach a critical field, then it goes normal. But a type 2 superconductor, it does that at low fields, reaches a lower critical field, then instead of going normal, it stays superconducting, but now the magnetic field enters the superconductor in the form of these fluxoids. These are quantized fluxoids where the magnetic field is the maximum at the center of the fluxoid, and you have a vortex of circulating supercurrent surrounding each fluxoid. Fluxoids are mutually repulsive, so they form a lattice. And in fact, interestingly, you can even get defects in the lattice. You can have dislocations, grain boundaries, and so on. To get a large JC, the fluxoid lattice must be pinned. If the fluxoid lattice moves, apply a current, you get a Lorentz force. Fluxoids move, of course, their cores are normal, creates heat, it destroys superconductivity. So you got to pin the fluxoid lattice. And the way you do that is with crystalline defects, things like dislocations, grain boundaries, and nanoscale, maybe normal second phases, and so on. Okay, so I became group leader of that little group in 1970, and the fluxoid pinning problem was something that our group worked on for about 10 years. In 71, 72, I spent a year at Harwell. We had exchanges with Harwell in the UK Atomic Energy Laboratory in their superconducting materials group. I happen to have my office in their plutonium building, which is a lot of other interesting stories, but I'm not going to talk about them now. Another sideline of my work on superconductivity was research on the element technetium. It doesn't occur naturally, only as a fission product, but it's got the second highest superconducting transition temperature for an element, exceeded only by niobium. But since it's radioactive, of course, we had to do all our work in a glove box. In those years, most of my publications were in physics journals. So I joined the American Physical Society, and I was actually elected a fellow in 1979. I think their criteria were not as high as they are today, probably. Okay, then I had a little change out of research. In 76, I was asked to be the technical assistant to Alex Zuckert, who was our laboratory director for the physical sciences. And this had been the fast track to rise in the management ranks at Oak Ridge, which at that time I thought I might want to do. So my first day, my first assignment for Zuckert turned out to be highly classified. I had to get special weapons clearance, Sigma 1 and 2. And I went around the lab learning about what we had to do. I couldn't take notes, I just had to memorize everything. And eventually had to work with our security people to debug conference rooms and so on. So sort of interesting. But besides that work, I ended up spending 2 years working for Zuckert. And while this took time out of my research productivity, I learned a lot of interesting topics at Oak Ridge. So I was involved with all the physics and chemistry and materials divisions and you know, how to find out all the neat stuff that was going on. But what I did learn was working strictly in management was not what I enjoyed doing. I looked at what Zucker did. He spent the whole day in meetings, including lunch. And he was a brilliant accelerator physicist. He'd done some really great work in spallation theory and stuff. And here he was, you know, of course, he had the power to tell people who could go on a foreign trip or who could get a big fancy piece of equipment. But what he did himself, you know, wasn't as interesting, I thought. Anyway, so that was worthwhile learning for me. When 78, I returned to the leadership of my former group on superconducting materials, but at that time, the late 70s, that's before the high TC oxides were discovered. Their kind of interest in superconductivity was waning. So we decided to move into another area. And after some study, we decided to get into the area of metastable amorphous materials made by non-equilibrium processing like rapid solidification. Our management approved this and the Department of Energy also did. And so this was a new learning experience for our group and of course for me. Went to a bunch of conferences on this topic and had some consultants in this area. In my last years at Oak Ridge, 1981, I was asked to take responsibility for a larger group when they were reorganizing the division. And I named this new group Alloying Behavior and Design. I think it still exists, to my knowledge. And this group included my task on metatable materials, and then tasks on alloy design by Dr. C.T. Yu, and fundamental mechanical behavior at elevated temperatures under Dr. Van Yu. And so with more managerial responsibility, I was asked to take the union carbide management system. Should point out, of course, I was a union carbide employee. All the national labs, the employees were not government employees. They're all either an industry or a university. And in those days, it was Union Carbide that ran it. Yeah, it later changed to Lockheed Martin and now it's Battelle. But in any event, I took the Union Carbide short management course, and then I was asked to take some courses in management at the University of Tennessee. But even though I was still doing more management, I could still do some research. And then in all TMS meeting, I happened to go into breakfast at the same time Hans Conrad did. And of course, I knew Hans slightly, and of course knew of him even when I was in grad school. And he'd recently become department head at NC State. And when we had breakfast, he asked me to give a seminar at NC State. And also, if I ever thought about teaching, he was planning to add some senior people to the faculty that he was trying to build up. And so I sent him my resume. And anyway, I guess I won't go into all the details, but anyway, eventually, this led to me joining the faculty at NC State in 1983. So I got advice from colleagues that I should start writing proposals as soon as possible, and I did that. And so I wrote proposals on intermetallics, on amorphous materials, metastable crystalline materials, and the mechanism of mechanical alloys. And I wrote them to the Department of Energy, NSF, NASA, and the Office of Naval Research, respectively. And to my pleasant surprise, I got all proposals funded. So I got off to a good start. In fact, I could even get a lot of equipment with these proposals. And so I've never had such good success since, but I was fortunate to always had continuous support from NSF throughout my career. So the research areas I pursued, and of course, a lot of these involved learning new concepts, amorphization by mechanical alloying and milling. Actually, just before I left Oak Ridge, I was the first one to show you can make an amorphous alloy by mechanical alloying. And that one paper, though it's not all as sophisticated as many others I've written, has the most citations of any. So if you're first doing something, you get a lot of citation. And then I worked on oxide superconductors for 6 years, short time on ferromagnetic materials, most recently high entropy alloys. So sources of my research funding have included NSF, DOE, Office of Naval Research, NASA, Army Research Office, Air Force Office of Scientific Research Triangle Institute. I had a subcontract on a large DARPA grant on thermoelectric materials. Hillsborough, I had several small grants from International Lead Zinc Research Organization, and I had a couple of subcontracts from Oak Ridge. And I've collaborated then with many colleagues here at NC State, probably most with Ron Scattergood, who's now retired. We were co-PIs on a number of proposals, both NSF and DOE and so on. Jade Ryan, Tom Brenner, Maury Balick, Chris Spontak, Justin Schwartz, Doug Irving, Yuntin Zhu, Peter Fedke, Angus Kingon, Dave Haas. All of these I was co-PI on various proposals. And then in a paper with Kobos, Nemenich, and Sitar on photovoltaic effects in silicon, nanocrystalline silicon. And then Rajiv Gupta, actually, who's now a professor here, but he got his PhD, made the materials in my laboratory while working for Professor Raman at Monash University in Australia. And Jim LeBeau did some very nice X-ray TEM work on a number of our projects, and particularly the thermoelectric ones. But outside of NC State, some of the people I've worked with, most proud of, David Turnbull, of course, if you know, he's one of the people in our field who's done so much seminal work, and he got interested in some of the work we were doing on the reduction of melting points. And so we actually wrote a little paper together, and he and Franz Papen invited me to give a seminar at Harvard, which again, one of the things I'm most proud of doing. Kunal Bulshan at the University of Cincinnati did some Mossbauer spectroscopy with me, and then Jürgen Eckert was at Dresden at the time, and Michael Zad Power, University of Vienna. We had one of these NSF Material World projects, and then I also already mentioned K. Singh Raman. Okay, to summarize then, I've sort of tried to summarize how the transition of metallurgical engineering to material science and engineering occurred. And while it took place initially in industrial laboratories, it then spread to academic departments, professional societies, and professional journals. And so the need for lifelong learning in our profession, illustrated by my career, starting with my education, and then followed by my work experiences, first at Oak Ridge National Laboratory, and then North Carolina State University. So learning new concepts and skills is also, while a lot of work, it's enjoyable. It keeps us mentally young. So at 85, I think I'm still more or less mentally young. I'm still teaching, although this is my last year of phased retirement, and I'm not sure how my students think about me, but as far as I know, I'm still okay. So I like this little quote from Robert Louis Stevenson's A Child Garden of Verses. The world is so full of a number of things, I am sure we should all be as happy as kings. So I'll stop there.
Good question.
I'm sorry?
You have a favorite research project among the list?
Oh, be hard to say. I guess early on, maybe studying amorphization by mechanical alloying, since I was sort of the first one to do that. And when I first presented at conferences, a lot of people didn't believe me. They said, well, you know, diffraction lines broaden when you mill them anyway, sort of. And so in a sense, I guess finally, a lot of people reproduced what I did and it got believed. But that's one, but you know, it's hard to really say because that's sort of the one I'm working on at the time tends to be the one that I like the best.
I can piggyback off of that.
Can you say what was the most challenging to work on? Projects or?
I think the fluxoid pitting problem at Oak Ridge has never really been solved. It's the problem, we could calculate interactions between the fluxoid and an individual defect, like a dislocation and so on. And that could be done fairly readily. But the problem was the fluxoid lattice. And then all the array of defects you have in a material. So the statistical problem of trying to solve that. Professor Labusch in Germany came the closest probably. But nobody's really solved the problem to my knowledge. And of course, toward the late 70s, people knew how to make good high J sub C superconductors anyhow. So the people who try to understand the mechanism, you know, there may be 6 of us in the world or something. So, you know, nobody cared. But, but I think that was probably the most difficult problem. I should point out that, you know, when I was doing this AC technique to measure J sub C too, I had to learn about a lot of electronic electrical instrumentation, which I wasn't really familiar with. I had to learn about, you know, signal generators and lock-in amplifiers and all that kind of good stuff. And that's not something that I had prior experience with.
What discouraged you going into management at Oak Ridge?
Sorry.
What discouraged you from going into management?
Well, I think, as I said, I saw what Alex Zucker did, you know, during his workday. And he was a brilliant guy, but he was in meetings all day. And while, you know, he had the power, if you will, and he made a little more money than we did. But, you know, what he actually did, it was not something that I thought I wanted to do.
Yeah, people thought when you took that job, you wanted to go up.
Yeah. Well, that's what these other people had done, the 2 people before me. And then Linda Horton after me, she ended up, you know, a big shot at DOE, right? And so on. So,
Jim Roberto.
yeah, and Roberto. Yep.
Carl, thank you. That was very inspiring. So, what are your thoughts about the future or your hopes for the future of the material science and engineering field?
Well, you know, we keep getting broader. First, we went from, you know, metallurgy basically to including ceramics and polymers, and now biological materials. And I guess my worry is that we might get too broad, and so we don't know enough about, you know, the specifics. But I guess so far it seems to be doing okay. A couple of years ago, I went to a workshop at MIT, which was basically on high entropy alloys, but you know, metals. And there the consensus was that actually the metals field was starting to rise again. So I hope that's the case. And you know, metals are still important. A lot of the elements are metallic.
Yeah, if you could go back in time, knowing what you know now, and give yourself a piece of advice when you were young, when you were a student, what would you say?
I'm not sure. I think I never had long range plans. I kind of went from one thing to another as it occurred. And I'm not sure. I think I've been lucky. I mean, I've looked at, you know, if I go into MIT, I think I would have done a lot better. I don't know. I got into National Academy, so I know a lot of people who went to MIT that didn't. So. Hey,
I've got a question. I'm curious about, so you've been at NC State for a while. I'm curious about the changes and evolution of the university that you've seen.
huh? Well, it's obviously grown.
Yeah.
And our department's grown. And I guess, you know, obviously the sophisticated equipment we have is more sophisticated. You know, when I was an undergraduate, we didn't have computers. I used a slide rule. And when I got to Oak Ridge, they just had the big mainframes. And then after a year or two, the HP came out with the little hand calculators. We weren't allowed to buy them because the division didn't want any competition with the mainframes. But after a year or so, the mainframes got so overused that they took that rule off. end ones, and then we had a Olivetti, I guess, that had paper tape or whatever. And then later on, we got other calculators, but things have changed dramatically. Of course, by the time I came here in '83, while computers have gotten a lot more sophisticated since then, at least we already had them then, so.
One of the other things I noticed in the research topics is that you obviously had to change, right? And that's where the lifelong learning. So you had to change, you had to move from superconductivity to something else. And change can be hard, right? When you're a researcher, you sometimes can fall in love with the topic or the idea of what the topic can produce in the future. So can you comment a little bit on that and what the driving forces were to make other areas?
Well, for me personally at Oak Ridge, I guess I saw that, we were kind of getting in a corner where there wasn't that much interest in what we were doing. And so for me, I think at least one member of my group was like you said, was not too happy about making a change, but most of us were okay with it. And I think we were all, we understood, we built a melt spinner and we learned how to do rapid solidification. I got Professor Deason down from Northeastern, who was an expert in rapid solidification. He kind of consulted for us, and well, we made an arc hammer, the early arc hammer, in order to splat our metal. He used like a soccer bat to hit the thing so that you maintained the pressure so it didn't bounce. And so, we wore a crash helmet, the guy who was doing the melting, and the other guy came down with the with the wooden rugby mallet, basically, and then we got more sophisticated, but
Research in your lab is similar.
What I understand, material science and engineering was just getting introduced as a new discipline in 50s and 60s. So was there sort of reluctance and doubt in academia in introducing it as a new field altogether in the universities?
By the time it was really going, I was at Oak Ridge, so I guess I didn't personally see too much what was happening. I know there was always a sort of a conflict between like the ceramists and the metallurgists and places like Illinois and so on. But I guess eventually I don't know, maybe it never went away. I know Maury would have liked to have more polymer people, but
And it's true.
yeah.
We have one more question.
Okay. On the thing that you got a lot of interest in, on mechanical alloy by milling for this purpose. How did you first get involved in any mechanical milling? Did that come from some ceramic work or something there, or?
Actually, I went to a conference in Monterey on amorphous materials, and we split up into various groups. And I got into one on processing, sort of. And we talked about various techniques for making amorphous materials. And Professor Bill Geeson from Northeastern, he was saying he was curious why nobody had ever tried to do mechanical alloying. And so I had that in the back of my mind and went back to Oak Ridge, and it wasn't right away, but maybe a few months later, I just said, let's give it a shot. And so I picked an easy glass former, a niobium nickel, and a good composition for making a glass. And I put it in, started milling it. Every hour we took out a sample, had it x-rayed. Lines kept getting broader and broader. Finally, they looked just like an amorphous diffraction pattern. And then we took it and we did DSE on it, and got the right value for the crystallization temperature and so on. And so I wrote this for a little paper in Applied Physics Letters that has now like 1,500 citations or something. And, so it's sort of serendipitous in a sense, but give Bill Geeson the credit. And actually, about the same time or earlier, even a couple of Russians had milled some intermetallics and made them amorphous. And then also, there was a student of Bill Nix at Stanford who was trying to mechanical alloy to make niobium-free tin. And he found after long milling times, the stuff went amorphous. And it was in his thesis. They never published it apparently. So I always, gave him credit that in a sense, they were the first ones, but they didn't recognize it. And Nix has always thanked me for giving them credit. So
In the interest of time, thank you.
got a lot of pictures, I guess.
Yeah. Awesome, great start. Great start to a long series.